All right, good morning. There's a great quote about software design from Tony Hoare, which, like all great quotes about software design, gives a very crisp diagnosis of your problem without giving you any real clue as to how to solve it. There's two ways of constructing a software design: to make it so simple there are obviously no deficiencies, or to make it so complicated there are no obvious deficiencies. The first method is far more difficult. Thanks, Tony. I should mention by that Tony Hoare is the guy who invented the null pointer, so he's a bit of an expert on deficiencies. I'm sorry? Quicksort, which thankfully doesn't have so many deficiencies. So the problem that Tony Hoare identifies is that because writing simple software is hard, and because requirements tend to be kind of complicated, we end up with a lot of non-obvious deficiencies. Well, how do we deal with those? How do we find those and fix them? Well, we make them obvious. It sounds easy. But we don't know how to make them obvious because they're not obvious. You're not helping. What we often do at the moment is unit testing. Does everyone here carry out some sort of automated unit testing? Almost everybody, okay. Those who don't, please start. It will make your life a lot easier. And unit testing traditionally has been sort of value-based, so you'll pass some known values into your code and make assertions about the results of your code. Make sure they produce the expected results. So for those who are not familiar with unit testing, that's the kind of thing that you end up with. This is the Xunit framework. The fact says that this is a test, and we're just making an assertion about if we apply a certain method to a certain value, it produces a certain result. Everyone comfortable with that? Yep, awesome. Value-based unit testing is really powerful, and it's got us a long, long way. It's hugely improved the quality of our software. But it does have some limitations, or it does have some difficulties. How do we know what values to choose? I mean, in my example there, I'm pretty confident that my square method works on the value 2, but I don't know if it works on the value 3 or 17 or 240. How do I know that the chosen values, the ones that I've selected to test, cover all the possible causes of bugs in my code? How do I know I've got reasonable coverage? I can inspect my code and try to work out where are the sort of the breakpoints, where are the seams, the edge cases that I need to make sure I pick up, or the subsets that I need to pick up. But remember, non-obvious deficiencies. It's not always clear to me just by looking at the code what might be going wrong. How do we know that we need to maybe choose different values or pick out some additional test values, test cases, as our designs and implementations change? None of this is obvious by inspection. What if we could test all of the values? Well, we might need a bigger computer. But that might be a bit expensive. What we can do is we can ask the computer to try lots of values very quickly and look for ones that expose flaws. We call this property-based unit testing. And in this idiom, instead of saying, here's an input value, here's what I expect the output value to be, you say, try it with as many of the input values as give you confidence, and here's what I expect output values to look like. Here's certain expectations I have of the output values. I can't say I expect the result to be 4 or whatever, because I don't know what the inputs are going to be. The computer's going to try different inputs. But I can say I expect it to have certain characteristics. Property-based unit testing is not a replacement for value-based unit testing, and we'll see some examples of that later on. It's something that complements it in trying to search a wider space for failure cases. It means you need to think differently about verification. You can't just run through an expectation in your head and go, okay, here's my inputs, here's my expected outputs, life's good. You need to think about what do outputs in general look like? What are their properties? What are their attributes? What are their qualities? It can drive you up the wall getting things right. Because you're looking for assertions that will work for any input, there are a lot of little edge cases that you won't think about, but the computer will. And writing your tests to work nicely with those can be pretty exacting. It is not infallible. It does not test all possible inputs, but it does try to get reasonable coverage by trying some, a number of random cases, and particularly trying common edge cases. And it can seem kind of magical when it sort of chews through your code and says, oh, I found something and I've reduced it to a minimal case. Here's 2 numbers that will break your beautiful algorithm. How did I miss that? Not obvious. So what does it look like? Well, I want to start by looking at a very simple example and try to think about how we translate a fact-based, a value-based test into a more generic property-based test. So I've got a method here that calculates the maximum of a collection of integers. And here is a test based on a sample input. And I'm going to assert that with that input, 487, the result is going to be 8. Why do I choose 8? Anybody? It's the second one. Okay. So this is going on your performance review, Bevan. I have an example of this later on, which in fact will show why you are wrong. Any better guesses? Why have I chosen 8? Power of 2? Okay, I've chosen 8 because it's the highest value in the collection. I mean, I know that may seem like a dumb thing to point out, but you guys are not helping. I want to break that apart into 2 things. Firstly, it's the highest value, and secondly, it's in the collection. What does it mean that it's the highest value? Well, it means there's nothing in the collection that is bigger than it. So I can write that as a property, as an attribute that that the maximum has. I'm no longer saying what the maximum is or what I expect the maximum to be. I'm saying what I expect it to behave like in terms of being the highest in the collection. Now I've got that as a property of the maximum. I can translate that into a property-based test, which means that instead of saying I want to try it on this particular input, 487, I want to try it on all possible integer arrays. And in the framework that we're going to look at, which is fscheck on Xunit, I do that by using property attribute instead of fact attribute, and by passing by having a parameter to the test method, which is the appropriate type for the input. So now when that runs, the framework is going to try a whole bunch of different integer arrays and verify that the test passes for each of those. And if it finds one that fails, it's going to try to reduce that to a minimal failure case. What about the other part of that sentence? The highest value in the collection. So we're saying that the maximum should be an element of the collection. The collection should have contained the maximum. And once again, by recasting that, I can now transform that in the same way to a property-based test. People see how that works? Does that kind of make sense? All right. Yeah.
So does that property attribute actually generate multiple inputs at one time, or do you need to run it multiple times to generate multiple?
So the question is, does that property attribute generate multiple inputs at one time, or do you need to run it multiple times? The answer is that it generates it runs the test method multiple times with differing inputs. So when you do a right-click run test, or you run it in the VS test runner or in ReSharper or whatever, instead of running that test method once with a random input, it will run it, say, 100 times with a bunch of random inputs. And we'll see that just shortly. So, going to get started, show you some demos. The framework I'm using is called FSCheck. It comes from the F# community. It works fine with C#. Don't get scared by the F# in the name. And it's got integration with the Xunit test framework, which is what I'm going to be using here. So here I've got my maximum calculator, and I've got some tests for it, some value-based tests. And there's my mouse. And if I run that test, bring up the output, you can see that test has passed. So that's a pretty promising indication that my maximum algorithm was correct. Except I overlooked one thing. The maximum algorithm I'm testing was written by Bevan. And it turns out there may be a slight flaw in that algorithm. Now, unfortunately, being naive, I just wrote my one value test case. But fortunately, if I look further down, I've got those property-based tests. All values are less than or equal to the max, and the max is one of the original values. Well, if I run that one, that still passes. But let's have a look at all values are less than or equal to the maximum one. Run that test. Well, that didn't go so well, did it? Because it generated a random array that looked like that, where my lucky property, my lucky thing of the first one being the maximum didn't happen to be true. But look at what else it's done. It's actually shrunk that down to get me a minimal test case, and it says, hey, if you'd fed the values if you fed the input -1, 0 into your max method, you'd have seen that it was wrong. You'd have found that non-obvious deficiency that Bevan put in there. So what about something like that? Is that going to work? Well, that succeeded. That passed. But now I've violated it must be in the original collection. So two bad implementations, one by me, one by Bevan. It's caught both of them. It's still worth having those value-based tests to kind of give us predictability about what the actual results are going to be. But we've found some characteristics that help to identify what it means to be the maximum and to feed in. Now we're able to feed in lots of values and verify they work in all circumstances. There is one nasty little wrinkle with this, though. If I firstly give you a actual reasonable implementation, but I don't have that little guard in there, my test fails because one of the random inputs that it throws at me is the empty array, and I don't actually know how to do a max over an empty collection. So I need to have that guard in there, but it's not quite nice because it means that I'm having random values thrown at me, but some of the time I'm going to just ignore the value and just return so the test looks like it's passed. Now in this case that's pretty benign because the number of empty arrays that the framework's going to throw at me is probably fairly small. So saying, okay, I'm going to ignore those ones. I'm getting maybe 95, 96 executions of my test rather than the full 100. But that's still a decent number. But if that filter was excluding too many input cases, then that will be a problem. I might only get, say, 30 or 40 executions of the test rather than 100. And that will create a lot more room for flaws to slip through. So we'll look at some solutions to that later on. Let's look at some other examples of how we can think about properties. So this is a test for reversing a collection. What are the properties we can think of about the reversed list? Well, it should be the same length as the original. So we can make a test for that. We'd expect that if you reverse the reverse, then you get back to where you started. So we can make an assertion for that. We would expect that if you concatenate a list and its reversal, then that becomes palindromic, which means that it is equal to its reverse. And snappy test name here. If I concatenate two lists and then reverse the result, then that should be the same as reversing each list and then sticking those reverses together back to front. That might seem like a fiddly thing, but it's important to be thinking about these things because otherwise, again, flaws can slip through. It's surprising how many of these tests pass with another rather flawed implementation. That shouldn't work, should it? And yet, if I run these, 4 of them passed, only 2 of them failed. If I'd not included some of those more fiddly tests, something could have slipped through. That's another reason, by the way, that using value-based tests alongside property-based tests is a really valuable technique. Because with the value-based test, you can kind of go, let me sanity check this by saying that here's a simple input, I expect this output, it's pretty obvious. And that will mean that even if you overlook some properties, you've still got kind of a backstop of sanity checking. And of course, now I can go into here, and clearly that is not a good implementation. Here is a better implementation, or a more plausible implementation. Is it right? To me, that is actually complex enough that I can't be sure whether it's right or not. I could throw test cases at it, or I could check on all of these properties that we've been talking about, run that, and that looks a bit more encouraging. And just to flag up, in answer to your question earlier, you can see when this reports, it's saying this has passed 100 tests, it's had 100 values thrown at it. If you want to do more, you can control that with the property attribute, where you can say max test equals, and put in a higher number there if you want to get further coverage. Obviously there you're trading off coverage for time. Does that all make sense so far? Any questions at this point? Cool.
Question.
Yeah.
Make it deterministic.
No, it is.
Pass at some times and fail other times.
It is not deterministic. So if you've got a edge case that only turns up very rarely, then it's absolutely possible that you could get a test run where it fails and you rerun it and it succeeds. That's why when it fails, let's just come back to one of these bad implementations. When it fails, it shows you, it logs the value that it failed with. And one of the things that is often a good pattern, I'll mention this later on, is a really good pattern to follow, is when you see a failure like that, that maybe is not reproducible, you suspect it may not turn up every time, is to capture that as a value-based test, use that input, write a value-based test around it, and that way you can ensure that that particular case gets exercised every time. You're not reliant on the random number generator to pick it up. Does that make sense? Cool. Right, so how FSCheck works is really pretty simple and pretty crude. It generates a whole bunch of test cases of varying sizes, whatever size means in this case. It might be, say, the length of a list or an array, for example, or it could be the magnitude of an integer. And it just throws those at your method. The default is to generate 100 test cases and throw all of those at your test method. If they all pass, then that's fine, the test passes. FSCheck says I'm done here. If any of those input values fail, then FSCheck starts trying to shrink the solution or to shrink the failure case. So for example, if it finds a 8-element array on which the test fails, it will try some 7-element arrays, or it will try an 8-element array with smaller values in it, and it will try to bring it down to a minimal case that means that it's easy for you to follow through in the debugger or to otherwise reproduce, so that it keeps it as simple as possible for you to diagnose it and remedy the fault. To do this, it relies on 2 bits of infrastructure, generators and shrinkers. It implements generators and shrinkers for a whole bunch of built-in types, so the common types like numeric types or strings or whatever, but also for arrays and lists and other common things. It infers generators for what it calls record types, which I'll discuss what those are in a moment. And you can extend that to custom types. If you've got a type that FSCheck can't work out how to generate random cases for, you can tell it this is how. So the generator is called to generate test cases. The shrinker is called when it's got a failure and just produces a set of smaller values. So let's have a look at that. So here I've got a vector class, and this is what FSCheck counts as a record type because it's got one public constructor which takes in all the values, and it's just everything else is immutable. It's just surfacing properties from there. And I want to do some tests about the length of this vector. Well, that's great. I can create some properties that describe what expectations I have. I'm expecting that the length should be non-negative. It should be at least as great as any component, any direction. And the triangle inequality should hold, which is that if you have 2 vectors that are stuck end to end, then the length of the composed vector should be less than or equal to the total length of the 2 vectors. And this sort of kind of works by itself. I'll give you a legitimate implementation, but we'll see that there's some problems. So if I run those tests, you kind of think those ought to all pass. Well, why not? Let's look at what the failure examples are. So our old friend, not a number. So because my vector components are doubles, FSCheck is going, great, I'm going to throw some nasty doubles at you. I'm going to throw nans and infinities and epsilons at you, and I'm going to make you squirm. And this is not very nice. In this case, we're relying on that generic, that inferred generator. And because it's saying, well, you said I can take any double here, great, I'm going to throw doubles at you. There are ways we can get around this, but they require a bit of customization. The other case where this is going to come up is where it can't infer a generator at all. One of the things I would like to do with my vector 3 is I would like to make it a struct, because really it's a value. It's a value type. But now it's no longer a simple record type because it's got two constructors. It's got the one that I declare, and it's also got the implicit default constructor that the CLR, that C# always provides for any value type. So now if I run test for that vector3 struct, it's not even going to get started. It's going to complain about the type custom type.vector3 is not automatically handled by fscheck. So what that means is that I'm going to need to provide a generator and a shrinker for that. And the way I can do that is at the class level, I'm going to say the arbitrary collection is this type of generators. Now, what is that generators class? Well, it's a thing that includes an arbitrary of the kind of thing I want to generate. So fscheck is going to look at that generators class, and it's going to look for members, static members, that are of type arbitrary of the type it needs to generate. Does that make sense? So this is just, it's going to use reflection. It's going to look at that class. It's going to say, I don't know how to create a vector3. Let me look in generators to see if I have an arbitrary of vector3. And if I do, then I'll use that to generate vector3 instances. So what does one of those look like? Well, we said that we had to have a generator and a shrinker. So here is a generator for vector3s, and here is a shrinker. What does vector3 gen look like? Well, it's saying I want to generate those components. So I want to kind of sample those from doubles and just return a new vector3 of the x, y, and z that have been generated as random doubles. But notice that I'm using this normal double, which hands off to arb.default.normal float. Well, what is that? Well, that is the built-in generator for the double type, except that it excludes crazy values. So it's saying, so by using normal float instead of float, I'm saying I only want actual numeric values. I don't want epsilons, I don't want infinities, I don't want nans. Just give me something sensible. So I'm going to cop out on those crazy values. So what this expression says is, hey fscheck, when you need to generate a vector3, generate a normal double, call it x, generate another normal double and call it y, generate another normal double and call it z, and then call the constructor for the vector3 struct, passing it x, y, and z. So that's how I get a random vector3 without crazy components. Yes?
Does normal double return a single value, or
And this is one of the warts that comes from being F# based. Normal float, so in C#, float means single precision floating point value. In F#, float means double precision, because why wouldn't you? So in fact, normal float, if I hover over that, let's see, you can see that does, or if you squint very closely, you can see that is actually returning doubles rather than singles. It's just a bit of an unfortunate piece of terminology. So can people follow how that generator works? I'm not seeing too much nodding. Do I need to go through that again? Would you prefer me to? Okay. So, to reiterate, we need to teach fscheck how to generate vector3s. We understand that? We understand why we need to do that. Okay. To generate a vector3, we need three things. We need an x, a y, and a z. We happy with that? Because once we've got those three things, we can feed those to a constructor, yeah? So how do we generate those three things? Well, that's where this link expression comes in. We've got a generator for doubles, and we're just going to call it 3 times, label the results, and pass those to the constructor. So we're leveraging the built-in double generator, which is this one, and we're just running that generator 3 times and sticking the results together into our custom type. Does that help? Awesome. What about the shrinking side? Well, in this case, we're always going to have 3 components, so the only way we can shrink things is by making the values get smaller. So if I've got a vector 3, which is a failing test case, I want to try to shrink that down to get a smaller failing test case. And I'm going to give fscheck a bunch of options for that, and it's going to explore down all of those alleyways and keep tracking down failing ones. So I'm saying if my x value is non-zero, if it's 0, then I can't kind of do anything with the x value, it's already minimal. If it's non-zero, then I'm going to shrink the x in 2 ways. I'm going to do a proportional shrink and a linear shrink. Why am I doing that? I'm doing the proportional shrink because if I've got something that's sort of way out in the 10 to the power 300, then subtracting 5 from it is not going to make a big difference. So I want to have something that's going to collapse it towards 0 pretty quickly. But I also want to be able to do once I'm in a small number, I want to be able to just step down rather than kind of converging very slowly towards 0. So I'm able to explore shrinkage in different directions. I want to do the same thing for y and for z. So for any given failure case, there could be up to 6 different shrinkages of that. 2 shrinkages in the x direction, 2 in the y direction, 2 in the z direction. And that will depend on your domain. So if you were dealing with some kind of collection, for example, you might shrink it by making the length of the collection smaller, by removing elements, or by making the values in the collection smaller. What you're trying to do is just gradually shrink that towards a minimal test case. And you can yield as many candidates as you like. In this case, I've yielded up to 6. And fscheck will just follow whichever ones you give it. And it will just keep doggedly pursuing ones that keep giving you test failures until it runs out of shrinkage options or none of the shrinkage options fail, which means you've reached a truly minimal test case.
Does doing it that way always ensure that it's the same values that occur? Are there situations where going through that shrinkage process could trigger some other deficiency?
So the question is, does going through that shrinkage process, does that could that trigger some other deficiency? So the reason for the failure could be a different reason from the original failure. That's kind of what you're describing? fscheck doesn't know anything about that. So all it's doing is it's saying, you've made an assertion, you've given me a property that you want me to verify is true, and it's not true for 10 to the power 50. And it's not true for 10 to the power 30. And if that's because it's hit a different flaw in your code, it doesn't know that. All it knows is the property is not true. So yes, you could absolutely expose a different bug on the way down, in which case you might fix that bug in the minimal test case, rerun the test and go, oh, but now my larger failure case is still a problem. It does, again, when it fails, it does print out both the original value and the shrunken value, so you can manually test both of those if you're so inclined. Right. So with those generators in place, I can now hook those up to my tests, my struct tests, and I can run those and they fail. And once again, they're giving me values. Why have they failed? Oh, because that's a stupid implementation of length. What about that one? That's interesting. I expected those to pass, but never mind. Curse of the demo. So one thing that I was hoping to illustrate, but for some reason I found a flaw in my own code, an unexpected flaw in my code. There are two implementations I've got here of length, one of which is using what's sometimes called the taxicab metric, which is if you were kind of only allowed to follow straight lines through space, and one of which is the more familiar Euclidean metric, which is the direct line. Sorry, when I say straight lines, I mean along the axis lines, one of which is the Euclidean metric. Those have got a lot of properties in common. It's actually quite hard to tell them apart with property-based tests. It's very easy to tell them apart with value-based tests. So again, this is one of those cases where having some value-based tests alongside your property-based tests can actually flag up that your implementation may be wrong even though the properties are all passing. Yes? Oh, rounding is, yeah. So I started working on this demo using doubles, and I kept running into problems with nans and infinities and rounding errors and all those things, and I thought, I've got to stop this. I've got to go back and do integers, and just never got round to it, and now it's come back and bitten me. So never use doubles for anything, especially anything in a demo. Right. But hopefully that shows you the principle of how we interact with custom types, how I'm able to write tests around custom types. Yes?
How many times does it try to shrink before it stops?
How many times does it try to?
Shrink.
It will keep trying to shrink until it no longer gets failures. So if for example, my implementation of shrinkage had been, say, to do -5 on each thing, and it had found a failure case at 10 to the power 30, it will keep going 10 to the 30 minus 5, 10 to the 30 minus 10, 10 to the 30 minus 15, and it would keep on going until either it reached a case where the test passed, in which case the previous one would be the minimal failure, or the heat death of the universe, or Windows rebooted, which obviously is long beyond the heat death of the universe because Windows. I work for Microsoft now. All right, so does that make sense to people? How we can use, yes, question.
In your generator, where you're just being in three random numbers, does the default generator try and pick some interesting combinations of numbers, like 0, 0 and a random number, whereas your one just sort of three uninteresting numbers?
That's a really good. So the question was, does the default generator, if I left the record type generator to do its own work, would it have tried to pick interesting and hostile combinations? That's a really good question. I don't know the answer to that. I suspect that it would probably just be generating uncorrelated random values to stick into the constructor. But it might be smarter than that. I don't honestly know. That would be an interesting avenue to explore. One of the challenges that we've seen with this is how do you actually think of good properties to test? And that's kind of relies on your knowledge of what the behavior is that you're expecting, what your knowledge of the domain or the algorithm that you're trying to create. But here's a few things that may get you started. There's some obvious ones from sort of design by contract kind of thinking. What are the invariants of the type? For example, if you've got a sorted list, then it should be sorted after any method call, so you can always assert that as a property. Post conditions of a method, for example, if you do an append, then the result of that should be one longer than the input list. You can use your knowledge of the domain. For example, what are the expected ranges? If you've got something which is maybe calculating a date or a year or an age, something like that, then you can probably say it's going to be within a certain range. For example, if it's an age, it shouldn't be negative. You might want to put a higher bound on that, or you might not, depending on what kind of industry you're in and depending on what kind of logic you want to put into your tests. There are things you should never see in a result. There's sort of that, well, it couldn't possibly produce, oh, it has scenarios. I'll give you an example of that later on. relationships between inputs and outputs. For example, if the input, take that square method, we could assert that if the input was odd, then the output is odd, but if the input was even, then the output was even. So they've got the same parity, if you like. Look for collection memberships. If you expect an output to be in a certain collection, whether that's the input collection or a different collection, you can make an assertion about that. And you can look for expected equalities and inequalities. Something is always less than us, your output is always less than your input, for example. Be sure to consider negative as well as positive scenarios. So if something shouldn't be the case, then find a property for that as well. And be cautious not to repeat implementations. When I was thinking about what properties would I create for the square method, I was thinking, I could assert that square is equal to x times x. That should always be true, shouldn't it? But you've repeated the implementation. You're testing your own code. You're just testing your code against itself. So be careful about that. It's okay to make assertions about expectations on those values, but try to make sure that those are worked through in a very different way, that they are qualities, they're attributes, rather than specifically value equality calculated in the same or very similar way. Okay. I want to give some illustrations of that kind of positive and negative scenario. I'm going to use, again, I'm afraid it's a rather unrealistic example of Roman numbers. How many people here work with Roman numbers? Oh, we've got one person. Awesome. Are you archaeologist? Oh, I'm disappointed now. But this is a domain where we can make, we've got certain, this kind of ties in with that thing we were talking about earlier about not wanting to have too wide an exclusion. Now, when I've got my Roman number algorithm, I'm going to find it's only going to work on certain values because the Romans could only count up to about 4,000, apparently. I don't know. Their numbers seem to run out about that stage. All these complicated numbers, but they involve Unicode characters. And I don't know how to use Unicode characters, and I think nor did the Romans. So I've got an algorithm for Romanizing and de-Romanizing, but my algorithm is restricted to certain values. Now, this makes it a little bit difficult to test, or to property-based test, because if I were to say, well, I'm going to try arbitrary integers, then the problem is that a lot of those arbitrary integers will be out of the range of 0 to 4,000, or 0 to 3,999. And that means that I've got that risk of it's going to throw a lot of random values at me. And if I just go, well, I'll just ignore anything that's outside my range, there's a good chance of ignoring a large number of the values it's throwing at me, which means that I'm not getting good value for money out of my 100 executions. So what I really want to do is have something that says, I want you to test with something that's in the range. I want you to throw random values at me. I want you to throw arbitrary values at me, but I want them to be in my 0 to 4,000 range, so I know that I'm actually going to be able to run my test and get a valid check out of it. Conversely, I also want you to be able to throw random invalid values at me so I can test that my error behaviors are correct in those situations. So how do I do that? Well, unfortunately, I can't just use an int there. So how do I do this? Well, I'm going to introduce a custom type. So if I define a type purely in my test assembly, my test project, called Roman convertible int 32, which is guaranteed to be within that 0 to 4,000 range, then I know that that when fscheck generates values of that type, I know they're legitimate inputs to my algorithm. How do I get that thing to work? Well, we're back into the world of generators. So I need an arbitrary of this custom kind of int32, which means I need a generator and a shrinker. And my generator is pretty simple. That gen.choose is a primitive. It's built into fscheck, and it will generate an integer in that range. So I'm just going to say from I in that generator, select a new Roman convertible int32 which is initialized to that value. So that guarantees that Roman convertible int32s will only be generated with values within that range. Similarly, when I shrink, I will get the default shrinker for this for the integer values, and then I will say, but I'm only interested in cases where you've shrunk it to something that I am happy with. So it's really just it's using those primitives, composing those primitives, and just wrapping things in a type so that I can distinguish, so that I can say that I only want things that are like this passed to my test. The type itself doesn't actually do any interesting work at all. It is really just a wrapper around an integer. But using that custom type forces fscheck to use my custom generator. If I was using a bald integer, then it would use its own integer generator. By using this custom type, I force it to use my generator. But that's all the custom type is for. It's not doing anything fancy. It's not a real type. It's only in the test assembly. So now I can write tests that just extract the underlying integer from that generated value and perform a test on it. In this case, my test is that if I turn that value into a Roman numeral and then parse that Roman numeral, I get back to the original case. I've also got some negative scenarios. My mouse has died. This is all going tremendously. So I want to say that if I create an invalid Roman number, then I can't parse it. So if I throw a random string of garbage at the Roman number parser, it should give me an appropriate exception. That means I need to be able to create strings of garbage which don't happen to be valid Roman numbers, because if the generator accidentally came up with a valid Roman number, then my test would fail unexpectedly. And again, this is just a wrapper for a string, for a Roman number, and I need a generator for that. And if memory serves, the generator was actually kind of scary because, yeah, so that's saying I want to use something that's got either an invalid character in it or it's got an invalid format, like having 6 I's together. So again, this is just using types almost as labels to invoke these custom generators and to separate those positive and negative cases. Yes? Why can't you use string as a parameter? Because in this test here, I'm asserting that if I give it an invalid value, I'm going to get an exception. Now, if I use string, a ball string, then it might accidentally generate the string I, which is a valid Roman number and would pass successfully and therefore would not throw the exception.
Surely you cannot do this 100 times. No?
I'm sorry, I can't hear you very well.
You cannot do this 100 times. You cannot accidentally generate correct.
No, it wouldn't, but it only needs to generate it once. Remember, it's going to throw 100 test cases at me, and it wants all of them to succeed. So you're absolutely right that the vast majority of random strings that were thrown at that method would indeed trigger the exception because they would be invalid. But, and that means the test would pass. But if it hit upon the string I in its set of 100, then the test would fail and it would go, aha, I found an input for which the property is invalid, for which the assertion fails. I have found a flaw in your code in that it does not assert, it does not throw on the input I. Well, actually, it's not meant to throw on the input I. So you're correct that it would have many correct cases, but it only takes one failure for FS check to go, hang on, you screwed something up here. And that's the value of it, in that it's looking at all those possible cases. Does that make sense?
Yeah.
Okay. I want to wrap up with a few patterns that we see quite commonly in terms of thinking of properties or how we construct property-based tests. One of the classic ones that we've seen, for example, in the Roman number example, in the string reverse example, and the example I mentioned here of, say, an encryption example, is inverse operation. If you've got two operations which are mutually inverse, one of which sort of cancels out the other, then a useful property to choose is that applying them consecutively, so if you apply one of them, then you apply the other, you should get back to where you started. And that shouldn't depend on the input, again, except for error cases which you need to rule out. You test that property by form the operation you're actually interested in testing, form the inverse, assert that you're back to where you started. Reference implementation is another interesting pattern. I said don't test against your own implementations, but if you've got something where, for example, you've got one of those designs that is so simple that there are obviously no deficiencies, then, but you can't put that into production for some reason, like performance, then that's possibly a good way of testing one implementation against another. You can have the slow implementation running in your tests, the slow but reliable implementation running in your tests, and then you can test the fast but scary implementation and see if they produce the same results. And if they always produce the same results, that gives you much higher confidence in your scary but efficient implementation. Another pattern is to look for relationships between results. So given two inputs, and you can have multiple inputs to an FS check method, I didn't show you that, but you can have multiple inputs. Given two inputs, you can say whatever the relationship was between those inputs, the same relationship or the converse relationship should hold between the outputs. For example, with that, with the prioritization algorithm, you could be looking at, if I've got two inputs which are, say, the priorities or some job information, then if A is less than B, then result of A should be less than result of B. Conversely, if A is greater than B, result of A should be greater than result of B. Make sure that you always, or that you test on as many passes as you can. You're trying to make an assertion every time you pass through this test. So don't go, oh, well, if it's less than, if the input is less than the output, then the result should be less. Because then you're not covering the other case. You should be making sure that no matter what relationship there is between the two inputs, you should be making an assertion about the relationship between the outputs, if at all possible. Make those 100 runs work for you. Never let anything slip by you. Another pattern that came up earlier in connection with your question was capture a failure as a value test. If there was something which was so subtle, so sneaky that you didn't realize it was a bug in your code, but the random generator found it for you, capture it, because as we've talked about, this thing is not deterministic. That might be a case that only comes up one run in 10. And therefore, you want to go, well, I want to make sure I don't get a regression on that. Let me capture that value and make sure I test it every damn time. So that if I get a regression on it, I know about it immediately, not 20 commits down the line when something else is run.
You do that with both the original failure and the strung failure?
I think that's probably your call. So when you diagnose what, so the question was, would you do that with the original failure and the shrunken failure? I think that's your call. I think you would probably want to look at both the original case and the shrunken case and go, do these look like, and this ties in with your comment, do these look like examples of the same bug? Or did they fail for the same reason? If so, probably not too concerned about capturing both of them. But if it looks like, well, hang on, this one failed for X reason, but when I shrank it, it exposed yet another bug, then yes, you probably want to capture both of them. But that will be a result of your diagnostic and your analysis of the situation. So what are the takeaways from this? Firstly, property-based tests complement value-based tests. They're not a replacement for value-based tests. You should still be sort of describing what your expectations are for common test values, just for your own sanity's sake and for readability in many cases. But the computer can often find cases that you never thought of. I've had numerous examples where I've used this technique and it's turned up errors in my code that I just didn't even think about. Just edge cases that I hadn't even considered testing for. It does mean you need to think in different ways. You can't just go, let me run the inputs in my head, figure out what the output should be, capture that, let it go. You've got to think about what are the common attributes of all outputs? What is the behavior I expect? What are the properties I expect outputs to have? And under what circumstances? Because often there'll be a valid range of inputs, for example, where you don't have expectations outside that range, and you need to exclude those from your test somehow. So you can be quite finicky to actually get the test to the point where it is only testing the things you want it to test, and only testing for the property that you want to make assertions about. But the important thing is you still need to think. Although this is kind of magical in that you put in a property, throws values at it, and suddenly a failure emerges as if the computer had worked it out all by itself, you still need to do a lot of thinking about what are the properties that I can do, what are the things that I need to capture, what is sufficient to actually pin this thing down. This is not a magic bullet. It will not work out all the bugs in your code for you, but it is a very powerful technique for finding bugs that you didn't know were there and you didn't think to look for. Thank you very much.